In the 1970s, classified under the codename Have Blue, U.S. aerospace manufacturer Lockheed Martin built a first-of-its-kind proof-of-concept demonstrator aircraft in a rather unique shape of a diamond. It would be the very first fixed-wing craft designed with the express purpose of avoiding detection by radar. Actual flight dynamics were of secondary concern. In fact, before the Have Blue project had its first test flight, engineers were doubtful the demonstrator could even fly, naming the prototype the Hopeless Diamond, a play on words referencing the famed Hope Diamond. Even though the project would go on to be developed into the first ever stealth fighter, the F-117A Nighthawk, the engineers wouldn't be entirely wrong. 2 Have Blues were built, but neither survived. DARPA began its search for stealth aircraft technologies under Project Harvey, named after the Invisible Rabbit in the 1950s movie of the same name. The United States intelligence community and armed forces worried that Soviet-made anti-aircraft artillery and radar-guided surface-to-air missiles could be a major threat to American aircraft. The Vietnam War and the Yom Kippur War, where Israel lost 109 planes in less than 20 days, proved the vulnerability of US and NATO aircraft when facing anti-aircraft attacks. The Soviet Union took to developing an integrated defense network during the Cold War, which a Defense Science Board study from 1974 claimed could be a major issue. One of the estimated wargame scenarios concluded that if the Warsaw Pact nations invaded and the aircraft loss ratio mirrored that of Israel during the Yom Kippur War, NATO would have its aircraft arsenal depleted 2 weeks into the conflict. Following the study, DARPA sent out secret petitions to 5 aircraft manufacturers asking for technology development with 2 primary questions: what signature threshold could make aircraft undetectable, and whether they could create such a thing. General Dynamics responded that electronic countermeasures were the best path, and talks with them were put to the side. Grumman and Fairchild did not indulge the petition. Douglas and Northrop agreed to work on the project and were granted $100,000 for research. Since Lockheed had not participated in fighter aircraft construction for 10 years, DARPA did not even reach out to them. Yet 2 of the company's leaders, Director of Science and Engineering Ed Martin and Skunk Works President Ben Rich, learned about the project from engineer Kelly Johnson and requested that the CIA let Lockheed Skunk Works contact DARPA. After an initial declination, DARPA agreed to let Lockheed participate in the contest, but without a government contract. Northrop, Douglas, and Lockheed were officially invited in 1975 to create an experimental survivable test bed by DARPA. Douglas walked out after having discovered the required threshold for an aircraft to be undetectable and deciding it could not be done. Northrop and Lockheed raced against each other on Phase 1 of the XST, which would test their full-scale model's radar cross-section and prove that their models could fly. Only one would win an extension of their contract for Phase 2. With $1.5 million to create the first part, the 2 companies took 4 months to build mock-ups that were then tested at the Radar Target Scatter Test Facility in White Sands, New Mexico. Their designs were very similar, but Northrop's model had more flat and angular surfaces. To test its design, Lockheed built a $187,000 pole to perch the aircraft on top of. In April of 1976, Lockheed won, as the Northrop XST featured a lower-side hemisphere radar cross-section. Despite Lockheed's accomplishment, the Northrop team was kept together to continue work in other areas. Eventually, Northrop's efforts would result in the battlefield surveillance aircraft experimental that ultimately led to the creation of the famed B-2 bomber. For Phase 2, Lockheed Skunk Works had to design and build 2 manned demonstrators. Codenamed Have Blue, the second phase saw Ben Rich taking $10.4 million in funds from Lockheed's management as the project faced budget cuts. The main goals were to minimize detection by radio wave, infrared technology, and eyesight, as well as to mitigate the aircraft's production of sound. Lockheed used leftover machinery from the C-5 program to assemble its HB-1001 and HB-1002 models. They were scheduled for completion by October of 1977, but after machinists went on a strike, the process was delayed and then overtaken by managers, who completed assembly of the first model in 6 weeks so that ground tests could commence in October. Construction happened in an experimental and flexible environment, with back-and-forth communication between managers, scientists, developers, engineers, and users. To reduce complications, Phase 2 focused on proving that the radar cross-section goals could be reached. To reduce costs, the prototypes were made small and simple, with an unpressurized cockpit, no mission equipment, and no capability to refuel mid-air. The second model featured coatings of radar-absorbing material, but the first did not. The half-blue prototypes were only about 1/4 the size of the future F-117A, with a 22.5-foot wingspan and low maximum takeoff weight of 12,500 pounds. The vehicles were designed and constructed with as few edges as possible for stealth purposes. While making the vehicle completely undetectable is impossible unless external radars are somehow interfered with, the technology and configuration of the vehicle could disguise its presence to the point that its presence would seem insignificant. Yet engineers and designers from Lockheed feared that the half-blue, hopeless diamond aircraft would not fly as planned. In fact, a document from the development team stated, quote, "Aircraft exhibits just about every mode of unstable behavior possible for an aircraft. The only thing it doesn't do is tip back on its tail when it's parked." To keep the plane stable, a control computer would have to constantly adjust minute flight controls. With half-blue, the United States was placing its hopes of maintaining Cold War aerial superiority in the countering of the Soviet Union's integrated defense systems. But despite successful anti-radar tests, much still rested on the ability of the small vehicle to actually take off and subsequently continue to fly. The plane was coated in a layer of iron paint and was cleverly camouflaged by 3 different colors, each in 3 different gradients, so that its edges and faceting would be undetectable by any accidental or spying onlooker. The part of the aircraft had been flown into the Nevada test site by a C-5 Galaxy plane, and it had been assembled on site. For testing, not only did the Hopeless Diamond have to prove its ordinary abilities, but its extraordinary ones as well. A second plane would be taking off behind it, playing the role of a hostile pursuer, so that the stealth capabilities developed during Half-Blue could be truly put to the test. With the relatively small expenditure of $35 million on the project, if proven to be functional, the Hopeless Diamond would not only pave the way for future aircraft and the defense of NATO nations, but it would also do so at a low cost. American pilots Bill Park and Major Ken Dyson were chosen to conduct the tests for Half-Blue, with Park flying the Hopeless Diamond for the first time. On December 1st, 1977, the Hopeless Diamond took off over Area 51 without complication. Ken Dyson followed on an F-15 Eagle, and their roles would reverse on January 17th of 1978. Only Park and Dyson would fly the Half-Blue prototype, with engineers making small additions and modifications after a couple of runs. The tests went on smoothly and secretively until the Hopeless Diamond's 36th test. On May 4th, 1978, Bill Park took off on the Hopeless Diamond as he had done for every other test flight, but that day would prove to be no ordinary test. The problems began during landing. Dyson, who was chasing the Hopeless Diamond, would later recall what happened, quote, "Just before touchdown, the airplane pitched up. It seemed it slammed down on the ground real hard. He raised the gear on the go-around, and when he tried to extend it on approach, only one of the mains and the nose wheel came down. All this time, gas was being consumed. I suggested he climb up to 10,000 feet for ejection. He started climbing, but the engine started flaming out from lack of fuel, so he ejected." Indeed, when Bill Park's attempts to lower the landing gear proved unsuccessful, he aborted the aircraft, which was blown to smithereens as it crashed. Park was injured but able to recover, although the concussion he suffered from the ejection ended his test flight career. The second prototype, the HB-1002, was about to be finished as an upgraded version. Unlike the first Hopeless Diamond, this prototype was painted gray, did not count on the flight test instrumentation boom that had been on the first's nose, lacked an unstealthy recovery chute for spins, and most importantly, was coated with radar-absorbent material, which increased its undetectability. It flew for the first time on July 20th, 1979. The only pilot to test this aircraft throughout its run was Ken Dyson. The aircraft was tested extensively for a little less than a month, as on its 52nd flight on July 11th of 1979, an engine fire broke out due to a hydraulic leak. The incurred loss of hydraulic pressure in turn caused intense pitch oscillations, which forced Dyson to eject. Dyson landed safely, but the second Hopeless Diamond was lost. Aside from the crashes, the overall results of the Half-Blue project were considered a major success by DARPA and led to the development of continuing aircraft. The Half-Blue project paved the way for Lockheed's eventual twin-engine stealth attack plane F-117 Nighthawk. The single-seat vehicle was developed under Skunk Works, Lockheed's Advanced Development Programs division, and was used exclusively by the United States Air Force. The core technology of the Nighthawk came from the Half-Blue proof-of-concept aircraft and was the very first operational stealth aircraft. The first flight happened at Groom Lake in Nevada in 1981, but the highly classified result of years of projects was not revealed until 1988. The F-117 was retired in 2008, but played key roles in the Gulf War, the NATO bombing of Yugoslavia, the only time one was lost in combat, and the Iraq War. Despite their official retirement, the planes continued to be kept in ready condition, and one was spotted flying in January of 2019. When model pilot Lieutenant Viktor Belenko failed to return to the Chugayevka Air Base after a training sortie on September 6, 1976, his superiors were puzzled. They believed he had likely crashed into the waves after his jet failed, but the Soviet Air Defense Forces chiefs eventually moved on. Unbeknownst to them, the well-behaved Belenko was already on his way to a new life with his jet in tow. As the Soviet aircraft suddenly appeared out of the clouds near the city of Hakodate, the Japanese Air Force officers could not believe their eyes, especially when the sizable jet with red stars landed on their runway. This was no ordinary jet. It was the Mikoyan-Gurevich MiG-25, the most feared and mysterious warplane in the West, and it was now in the hands of the enemy. On September 6, 1976, Lieutenant Viktor Belenko arrived at a briefing meeting to review that day's flight plans. Belenko was based at the Soviet Air Defense Chugayevka Air Base in Primorsky Krai, the Russian region nearest to the Sea of Japan and only 400 miles away from the enemy nation. That day, several of the squadron's aircraft were set to fly east over the sea to meet up with Soviet Navy ships. The ships would then launch target drones so that the warplanes could practice with their missiles. Feigning attention, Belenko sat motionless while carefully planning his own mission, calculating times, speed, distance, fuel use, and potential obstacles. During a subsequent routine physical exam to ensure he was in good shape for the mission, Belenko blamed his high pulse and blood pressure on an exhausting morning workout. Joining his fellow pilots, Belenko then boarded his MiG-25, one of the most powerful fighter jets in the world. Born just after World War II, Belenko had been a model Soviet citizen his entire life, joining the military service at a young age and qualifying as an elite fighter pilot with the Soviet Air Force. Still, the 29-year-old had grown disillusioned with his own fractured personal life and with the Soviet regime, so he had started questioning whether the Americans were as evil as the communist regime constantly suggested. Thus, he planned to escape aboard his MiG-25. Shortly after taking off with his fellow pilots, Belenko broke formation. Within a few minutes, he was flying his unarmed MiG-25 with a full tank of gas over the ocean waves, heading straight towards Japan while staying as low as 100 feet to evade both the Soviet and Japanese radars. Once he was deep enough into Japanese airspace, Belenko took up the aircraft to 20,000 feet. His plan was to be noticed by their intelligence. Flying by memory and guesswork, the Soviet pilot actually intended to reach Chitose Air Base. Still, low fuel forced him to land at the nearest available runway. Belenko suddenly spotted one, but it was too short, and the asphalt ran out as he performed the landing maneuvers. The jet then plowed through hundreds of feet of soil before finally coming to a halt. The pilot then fired 2 warning shots before slowly climbing out of the cockpit as motorists on the road near the airport began to gather around such a strange sight. Minutes later, Flight Lieutenant Viktor Ivanovich Belenko of the Soviet Air Defense Forces made an important announcement. He wished to defect. However, Belenko was not at Chitose Air Base, nor at an embassy. Instead, he was in the Japanese provincial airport of Hakodate, the capital city of Oshima Sub-Prefecture. As the airport officials finally reached him, they realized they were dealing with a defection and the surrender of a Mikoyan-Gurevich MiG-25, the most secretive aircraft the Soviet Union had ever built. The Mikoyan MiG-25 was one of the Soviet Union's closest guarded secrets. Introduced in early 1970, the jet was built in response to a series of American warplanes recently brought into service, such as the F-108 fighter plane, the SR-71 Blackbird, and the massive B-70 bomber. The model, which NATO called Foxbat, was first spotted that same year by spy satellites, which captured images of the new aircraft being tested in secret. An enormous fighter plane, the West's most significant concern regarding the design was its large swept-back wings. At the time, U.S. intelligence knew virtually nothing about the new aircraft's capabilities. Believing this feature to be a clear indication of supermaneuverability, American officers thought the aircraft could be the best dogfighter in the world. A year later, after a physical sighting near Israel, a local radar picked up the signal of the new aircraft while accelerating to Mach 3.2, more than 3 times the speed of sound. This puzzled both the local Air Force and the Americans, who were called to see the evidence. Soon, rumors about the aircraft's true capabilities and specifics started circulating, with some saying the type had the most impressive state-of-the-art radar in existence. Suddenly presented with a Soviet fighter that could potentially outrun and outmaneuver anything in the U.S. Air Force arsenal, the MiG-25 became the most feared aircraft in the world. 5 years later, the Japanese government suddenly had a Soviet pilot and the world's most mysterious fighter jet in its hands. The Hakodate airport then became a hive of Western intelligence activity. The aircraft was dismantled and moved by a cargo aircraft to a Japanese Air Force base on September 25th, and top brass invited a large team of U.S. officers and scientists to examine the warplane extensively. Soon, aviation experts inspecting every piece of the aircraft were able to find out the truth about the elusive warplane. Its large radar, once thought to be the latest in the game, was years behind U.S. models. Still, while its elements were outdated, its materials made it virtually jam-proof, a feature that was not available on American radars at the time. Another massive problem was its 2 enormous engines. While each was capable of 11 tons of thrust, enough to break the barrier of sound by 3 times, such speed put considerable pressure on the motors. The scientists soon discovered that when flying above 2,000 miles per hour, the wind's force would be so significant that it would start eating up parts of the engine itself. As such, the Westerners concluded that the MiG tracked by Israel in 1971 at Mach 3.2 was probably destroying its own engines while showing off, and was quite lucky to return safely to base. After a thorough analysis, the Westerners also realized that the MiG-25's capabilities were wildly overestimated, and the most feared aircraft in the world was nothing but a paper tiger. News of Viktor Belenko's defection reached the Soviet Union in no time. In response, the Russian embassy in Tokyo released a fuming statement, claiming their right to protect military secrets and demanding that the secret aircraft and the pilot be returned to the motherland. Still, the Japanese ignored all requests, and some officials even shot a few Russians trying to get to the aircraft. Belenko did not return to the USSR and was given American citizenship. In the US, the pilot became an aeronautical engineer and consultant to the Air Force. Once the American intelligence had gathered all the information it wanted about the MiG-25, the aircraft was reassembled and loaded on a boat for its return to Russia, along with a $40,000 bill for shipping costs and runway damage. However, the debt was never paid. Upon the aircraft's arrival, Soviet experts soon discovered the extent of the West's knowledge about the previously classified aircraft. They then noticed some damage to the systems and avionics, including the radar, which had noticeably foreign fuses attached to it. The engineers determined that in addition to running the engines several times, the Westerners had reverse-engineered all the operational equipment. The 1976 incident set off a flurry of Western media publications criticizing the MiG-25, describing the design as rudimentary, engineering archaeology, and flat-out obsolete. Still, the press conveniently hid some of the improved features, including mentioning that the MiG-25 airframe worked perfectly at extremely high temperatures and could be easily and quickly repaired by standard repair personnel. After reverse engineering the MiG-25, the U.S. Air Force embarked on one of its largest and most effective projects, the McDonnell Douglas F-15 Eagle. An all-weather tactical fighter that is still in service, this type was built to succeed the MiG-25 in all capacities, including its speed and maneuverability. On the other side of the world, the Soviet government, the Ministry of Defense, and the Ministry of Aircraft Industry also took resolute actions to improve the aircraft, as well as all secrecy protocols. 2.5 years after Belenko's defection, an improved MiG-25 PD entered production, and the Soviet Air Force built 1,000 additional models. Even Sukhoi, Mikoyan's local rival, built the Su-27 series in response to the debacle. But since the MiG-25's concept was still compromised despite the improvements, the Red Armed Forces subsequently developed the MiG-31 interceptor aircraft. A complete realization of the MiG-25's potential, but with more modern capabilities, the MiG-31 entered service a couple of years before the end of the Cold War and remains in service with the Russian Air Force. In contrast to its predecessor, insightful knowledge about the inner workings of the MiG-31 remains close to none. Grumman's experimental aircraft X-29, with its forward-swept wings, appeared almost as if it should be flying backward. The unusual configuration sought to test new canard control surfaces and advanced materials to improve maneuverability response at a high angle of attack. It was flown together by NASA and the Air Force as a testbed for joint interests. While promising and positively reviewed by test pilots, the aircraft's new technologies made it one of the most aerodynamically unstable planes in the history of aviation. An incredibly complex system was needed to continually calibrate the controls to keep the X-29 in the air. Still, the promise of the potential new technologies was so enticing that even the Russians couldn't help themselves from trying to replicate them. The X-29 project started at the height of the Cold War and involved a collaboration between NASA, the US Air Force, and DARPA, the Defense Advanced Research Projects Agency. The aircraft company Grumman was tasked with creating this ultimate fighter aircraft. In 1981, DARPA, the R&D wing of the DoD, awarded a fixed-price contract to Grumman. They constructed 2 planes as part of the deal. Grumman would carry out 4 test flights. After successful testing, they'd hand the aircraft over to the US military. Design work commenced in 1984. This was to be the first considerable experimental project of this nature in decades. The plan called for a forward-swept wing plane, which visually stood out. Actually, they hoped these unique characteristics would outperform other modern aircraft. Before this project, the United States prioritized aft-swept wings due to structural limitations that prohibited different wing types. Yet most of the drag benefits were independent of the direction in which the wings pointed. The Germans worked extensively with this type of aircraft. They abandoned the project during the Second World War, in part due to the war's outcome. The primary design challenge Grumman faced lay in how to prevent the wings from twisting due to their direction. If that wasn't challenging enough, it was incumbent upon the team to keep the aircraft light. They needed to develop stiffer wings that required new materials. 2 airplanes built by Grumman modified existing F-5A Freedom Fighter airframes. They also proposed modifications to the General Dynamic F-16 Fighting Falcon, but this idea was shot down in flames. The new shape of the X-29 aircraft presented several challenges for American engineers. Among these was the matter of weight. The forward-facing wing designs would be subject to extreme twisting force by headwind. This threatened to break them were they not reinforced. Making them out of metal was out of the question, because the added weight would kill the prospective performance. As a solution, they decided to use a new mix of composite materials, which have since become standard for both commercial and military planes. The aerodynamic lift would twist the wing's leading edge upward, which would lead to structural failure. Anisotropic elastic coupling solved the problem by bending and twisting the carbon fiber composite material without compromising weight. The X-29 introduced a laminate, which could produce coupling between torsion and bending. This resulted in the increased lift. The bending loads would force the wingtips upward. Furthermore, the coupling resisted torsion loads, which would otherwise twist the wing to higher angles of attack. The leading edge would be turned downwards, and therefore solve this problem. By reducing lift, the loads decreased, as well as preventing aeroelastic divergence in the material. Throughout development, estimates of the proposed aircraft showed 35% instability. In contrast, other planes at the time had a maximum of 5% instability. This new structure produced an unprecedented challenge, which would arguably make the aircraft unflyable. A few test fighter pilots became anxious even before the prototypes were completed. Determining the problem early allowed the team sufficient time to tackle it. Knowing that without a ballast equal in weight to a car on the nose of the plane, they would not be able to stabilize the aircraft, they decided to approach the issue from a novel angle. The design choice, referred to as a three-surface aircraft, employed three longitudinal controls through the canards, forward swept wings, and aft straight control surfaces. As a result, the canards and wings reduced drag, both wave and trim. The strakes provided trim wherever the center of gravity was off, and therefore reduced drag. Without a failsafe system, this configuration and the center of gravity behind the aerodynamic center eventually led to an extremely unstable plane. The engineers decided to use forward canards and rear flaps, controlled by a trifecta of redundant computers. Stability was achieved through the flight control system, capable of making 40 corrections a second. The computer system, backed by three equally redundant analog computers, rechecked and corrected its own assessments, exponentially reducing the probability of errors. While any of the three machines could theoretically assist in allowing the aircraft to fly, redundancy made the system nearly infallible. Each computer sent measurements and made quick assessments, which were weighed against the two others. Any malfunctions were immediately detected. At the time, calculations by experts concluded that the three-computer system was as unlikely to fail as the regular mechanics on a conventionally arranged plane. Still, the unlikely possibility of system failure was terrifying. NASA's Armstrong Flight Research Center historian Christian Gelzer stated, quote, "The engineers concluded that if all three flight computers had failed together, the airplane would have broken up around the pilot before the pilot had a chance to eject." Furthermore, he claimed the system was absolutely vital. Quote, "It was unflyable, literally, without a digital flight computer on board, which made connections to the flight path 40 times a second." Finally, the aircraft was completed, and the first X-29 was ready for testing. Its maiden flight took off out of Edwards Air Force Base on December 13, 1984, by Chief Test Pilot at Grumman's, Chuck Sewell. It was the third plane to fly using a forward-swept wing, and the first American aircraft. The technology had been previously implemented on the German planes Junker's Ju-287 in 1944 and the HFB-320 Hansajet in 1964. However, the X-29 achieved what no forward-swept wing plane achieved before: supersonic speed. Pilots who flew the X-29 had nothing but positive things to say of the experimental testbed. Due to its fantastic thrust-to-weight ratio during takeoff and minimal turbulence, pilots agreed that other aircraft paled in comparison. After pilots successfully performed 5 consecutive flights in a single day, the plane was approved. Following its maiden flight, the X-29 commenced a 4-month NASA test program. Despite complications and initial challenges regarding the instability of the aircraft, the three-computer systems proved invaluable. The plane was reliable and, even more critically, deployable. By August 1986, the plane flew multiple times for research missions with durations all over 3 hours. However, the first model of the aircraft had no spin recovery parachute, since all test flights avoided any maneuver, which would take the plane out of a controlled flight. Seeing this drawback, the second model was equipped with a parachute and tested for high angle of attack. It proved to be maneuverable up to 25 degrees, but reaching a maximum angle of 67 degrees. Between 1984 and 1991, the two X-29 planes flew 242 times. The Dryden Flight Research Center published an internal report on the new technologies and techniques shown by the X-29. New applications of previous technologies, such as the aeroelastic tailoring, improved the plane's control of structural divergence, aircraft control, and handling. Its success mostly relied on the three-surface longitudinal control and the advancements made with the second model regarding the high angle of attack. Regardless of the program's future, the X-29 had proved essential data for military aircraft production. Experimental as the X-29 was, the forward-swept wings weren't uncommon. During testing, the American intelligence community discovered Russia had started work on a similar, yet bigger aircraft. On September 25, 1997, the Russian Sukhoi Su-47 took off for its maiden flight. The forward-swept wing experimental fighter was also supersonic and included advanced radar technology and an internal weapons bay. It was in development since 1983, but the project was postponed by the fall of the USSR. The plane was nicknamed Berkut, Russian for Golden Eagle, and had dubiously similar design features to the X-29. Due to the timing and details of the project, NASA historian Gelzer commented, quote, "It's hard not to draw that conclusion, that they saw this and they decided we'd better figure out if it works as well." Yet the Sukhoi plane had some notable differences, which proved it a more impressive fighter. Twice the size of the American model, the Sukhoi was built to be an operational fighter aircraft rather than an experimental test bed. Still, only one plane was ever produced. During development, the supersonic jet demonstrated great agility and maneuverability. This was due to the forward-swept wing, which would inspire a new generation of Russian planes. In 2015, the Russian Design Bureau started testing the SR-10, which was eventually cancelled due to a lack of funding. Plans for the next generation of Russia's jet fighters featured several technologies researched during the Soviet copycat project. The Sukhoi Su-57, intended to replace the Fu-27 and MiG-29, is slated for 2020 production. It's rumored to feature supercruise, stealth technology, and super maneuverability. Supposedly, it will herald the next generation of avionics for both ground and naval defense in Russia. The X-29 broke more flight records than any other X-label experimental program. Still, it was scrapped soon after in 1992. The general consensus among aviation historians and enthusiasts is that the cancellation was due to the Department of Defense prioritizing newly researched stealth technologies for aircraft. The forward-swept wing design of the X-29 was incompatible with this new focus. Still, others believe the seemingly superior Russian clone Sukhoi Su-47 intimidated the United States and led the Department of Defense to gravitate toward more ambitious projects. The complete aircraft was exhibited at the Research and Development Gallery within the National Museum of the U.S. Air Force at Wright-Patterson Air Force Base in Ohio. A second X-29 was sent to the Armstrong Flight Research Center at Edwards Air Force Base. The experimental X-29 now serves as a wonder to museum goers. In the 1970s, Soviet engineers conceived the ideal stealth fighter. It was the middle of the Cold War, and the nation needed a modern, multifunctional fighter. As Sukhoi developed the next-generation S-57, the company kick-started a new era in aviation for the country. But never did they foresee that the Soviet Union would fall apart before their dream stealth fighter came through. The cuts in funding and multiple delays dragged the project into the 2000s, but the Sukhoi 57 was still ready to serve its country, albeit in a different shape. It didn't matter if the S-57 was conceived 40 years ago. It was more than ready to compete against the finest American aircraft. In the late 1970s, the Soviet Union outlined the requirement for a next-generation fighter that would enter service in the 1990s. The need of the failing nation called for a multifunctional fighter that featured advanced ground attack capabilities. Two programs branched from the original appeal, namely the multifunctional and the light frontline fighters. While Mikoyan was selected for the MFI and developed the MiG 1.44-1.42, Sukhoi started a program of its own. Though not an official participant, the company developed the required technology for a next-generation fighter that led to the forward-swept-wing S-32, later known as S-47. However, when the USSR dissolved, the MFI was repeatedly delayed due to a lack of funding. Making matters worse, the Russian Ministry of Defense canceled both initiatives. Soon after, the ministry initiated the Prospective Aeronautical Complex of Frontline Air Forces program, or PACFA, as a supposedly more modern and affordable alternative to the older concept. Due to the emerging country's financial struggles in 1999, the project's main objective was to produce a single multi-role fifth-generation fighter to replace both the Su-27 and the MiG-29. Sukhoi's and Mikoyan's approach to the new competition differed in fundamental ways, with Mikoyan's smaller E-721 eventually giving way to the comparatively larger and more capable Sukhoi T-50. By the spring of 2002, Sukhoi emerged as the winner and the lead design bureau for the new fighter, and the ministry approved the conceptual design 2.5 years later. Government funding eventually increased, and the development stage was finally complete. Now the construction of the first prototypes could begin. In 2007, the T-50's maiden flight had to be postponed due to unspecified technical problems. And 2 years later, Air Force Commander-in-Chief Alexander Zelin had to acknowledge that problems with the engine remained unsolved. After several delays, the first taxi test proved successful, and in January of 2010, the fighter took its maiden flight, with test pilot Sergei Bogdan at the helm. Slowly but steadily, the program moved on, with a total of 10 flying and 3 non-flying prototypes for preliminary flight tests and state trials. However, another issue soon emerged, when the initial prototypes demonstrated poor fatigue life and formed early structural cracks. The aircraft required structural redesign, including an increase in composite material, a reinforced airframe, an elongated tail sting, and an enhanced wingspan. The plan initially contemplated 6 prototypes before aerial production, but the 6th flyable one was part of a second stage of refurbished aircraft. Moreover, the last 2 flying prototypes were test articles of the final Su-57 production aircraft, fully equipped with its mission systems on board. Still, the structural redesign increased the standard takeoff weight to 25 tons, despite the reduced weight growth of the second stage. Thus followed a series of accidents during testing that further delayed the program. In fact, the delivery of the first production fighter was pushed back from 2015 to 2020. The T-50 prototype endured many setbacks leading up to the adoption of the final Su-57. In a 2011 public showcase, not one but 2 airframes cracked during flight, despite the imposed 5G restriction. In addition, the models also suffered from engine problems, such as a compressor stall. Then, in 2014, a prototype had an engine fire, and 5 years later, another one crashed in eastern Russia during factory trials prior to its delivery to the Russian military. The company's CEO resigned after the factory incident, further setting the program back and adding to the fighter's rocky history. But for all its setbacks, Russia boasts that the Su-57 has G-limits surpassing 9.0 and Mach 2 capabilities. Also, the aircraft is reportedly armed with an internal 30mm autocannon and can carry missiles and bombs in a dozen hardpoints, 6 internal and 6 external. What's more, the fighter features advanced avionics, such as a powerful radar, infrared search and track, an ultraviolet missile approach warning system, and an electronic countermeasure suite. Also, its electronically scanned array, located on its so-called cheeks, provides better situational awareness and enables advanced maneuvers that could come in handy during a dogfight. Finally, the onboard infrared search and track sensor upgrade helps with missile targeting and can be resistant to enemy jamming. In other words, the fighter can blind an incoming missile with a modulated laser beam that confuses the heat-seeking projectile. Under NATO designation, the Su-57 was given a fighter name and was dubbed Felon. Russia has praised its Su-57 as the most capable 5th-generation fighter in the world. Not only that, but it assures its fighter could outcompete the American F-22 and F-35. In fact, several Russian defense experts claim that the new fighter has extremely potent weapons and radar elements, and that its electronic warfare system is cutting edge. Still, the Russian military is promising a lot and not delivering. One culprit of the advanced fighter's sluggish progress is its dainty engines. Although the engineers originally wanted to power the aircraft with the latest Izdeliye 30 engine, the model wasn't a good fit, and the designers were forced to fall back on the older but reliable Saturn AL-41F1. As intriguing as the Su-57 program is, there's no doubt that it has hit a few bumps, with equipment failures, finicky engines, a fair deal of delays, and the inevitable cost overruns. However, the endeavor does promise to compensate with innovations, such as the ability to soft-kill incoming missiles, thus improving survivability. That is, if the system ever works adequately. While the program has been highly touted, as of 2022, the country has less than a dozen operational Su-57s. Still, it has 22 planned for the next 2 years, and a total fleet of 76 by 2028. In early 2018, 2 felons were seen operating near Khmeimim Air Base in Syria. Several reports state that they were later joined by another 2 Su-57s 3 days later. On March 1st, the Minister of Defense, Sergei Shoigu, confirmed that a pair of fighters spent 2 days in Syria carrying out trials, albeit not for combat. And towards the end of that year, the Defense Ministry shared a video showing the aircraft operating over the country. The footage didn't show any combat or even weapon deployment, and several analysts insist that claims of the operation in Syria could be part of the developers' push to market the fighter to foreign nations. Admittedly, developing a modern stealth fighter is extremely expensive, not taking into account setbacks and delays, let alone the amount the Su-57 experienced. Evidently, Russia is expecting to recoup some of the cost of its native design by selling the export version, the Su-57E, to foreign militaries. This is common practice for aircraft, tanks, helicopters, and small arms, given that Russian-made equipment is generally cheaper than Western machinery. Still, the model has been unsuccessfully pitched to several countries on multiple continents. At some point, the United Arab Emirates showed interest in the fighter, but did not dare sign a contract to avoid U.S. sanctions. Likewise, Iraq expressed interest in the purchase, but made no official deal. On its part, India signed early in the development, but claimed that the fighter did not meet its requirements for stealth and avionics, and eventually opted out of the contract. According to reports, only Algeria has signed an order for 14 aircraft and expects to receive its first Su-57 in 2028. As of 2022, Russian state-run media assure that the new fighter is flying missions in Ukraine, although some experts suspect that the felon is only firing standoff missiles. Brent M. Eastwood, the defense and national security editor of the 1945 Foreign Policy web magazine, added that the Su-57 may be firing outside of Ukrainian air defenses, and maybe even in Russian airspace. The fighter's limited use must have let down the Russian military, which expected to outcompete the most advanced American fighter, as well as its own neighbors. Now, the Russian defense industry will undoubtedly suffer from Western sanctions, and will be hobbled in the coming years. With all the money and resources allocated to pay for the current conflict, experts wonder if the fleet is ready for combat at all. Eastwood believes Russia will probably hold its valuable fleet back, allowing the aircraft to fly only when out of surface-to-air missile range. The author ponders, quote, "If the Russians were to gain air superiority early in the war, as they planned, the Su-57 may have taken on a wider role in the fight." The analyst also doesn't believe the felon is as stealthy as the F-22 or the F-35, nor even the J-20, claiming that total advancement is not assured, and that the aircraft is probably better referred to as having stealth capabilities. Despite the optimistic production targets, the Su-57 will probably suffer many more delays, even before broader manufacturing kicks off. Until then, the expert guesses, quote, "Russian media will likely spin the airplane as a better version of American and Chinese stealth fighters." It's been called the most outstanding military aircraft never flown. In many ways, the British Aircraft Corporation TSR-2 bomber was ahead of its time. Plans called for it to serve as a supersonic nuclear strike option, capable of flying at an altitude of 200 feet to penetrate deep into enemy airspace. Test pilots claimed the TSR-2's flight characteristics were outstanding, and a Royal Air Force evaluation of the program suggested that there was no doubt that it could meet all of its mission goals. Yet after its first flights in 1964, the program was suddenly cancelled only a year later. Amid rumors of a conspiracy, all of the working prototypes were destroyed. The USSR introduced surface-to-air missiles in the late 1950s, making many NATO high-altitude planes highly vulnerable. In 1959, the USSR used its S-75 Dvina Sam to shoot down an aircraft for the first time, a Taiwanese English electric Canberra plane, purchased from the United States. Operational requirement. Such a particular Soviet advancement presented an operational threat for which the UK stressed to respond to. In 1955, the Ministry of Supply began collaborating with English Electric to define the necessary parameters for the creation of a new aircraft that would replace the Canberra. Their studies yielded a list of requisites sent to several aircraft manufacturers in March 1957 under General Operational Requirement 339. The requirements were quite demanding and ambitious regarding the technology available back then. They wanted an all-weather, day and night, supersonic, long-range aircraft capable of flying at both low and high altitudes and of delivering nuclear or conventional bombs. Aside from asking for Mach 2 or higher, the British also wanted a plane capable of either short takeoff and landing or vertical takeoff and landing. However, the epoch's conventionalism considered air bases and runways to be the first things to go in upcoming wars. As a result, the requirements called for an aircraft that could take off and land on either rough fields or open areas. The deadline for submitting proposals in response to the insanely intense requirements was January 31st, 1958. The first challenge along the aircraft's development was the release of the 1957 Defense White Paper by Defense Minister Duncan Sandys. In it, he claimed that ballistic missiles would be the primary weapon in future wars, pushing manned combat toward obsolescence. While these claims would be discredited by future combat, at the time these statements resonated among the public and political spheres. Ballistic missiles were attractive not only because they're unmanned, but because they can offer significant savings if compared with other technologies. The 1957 Defense White Paper sparked a debate that would continue for years, with Royal Air Force members passionately speaking and acting in favor of the project requested in GOR 339. The very request for an aircraft was haunted by complications. In September 1957, only 4 months before the submission's deadline, the Ministry of Supply informed all the aviation companies that only multi-company proposals would be considered. This was a move by the government attempting to force mergers due to the large number of competing companies and the project's decreasing availability. Furthermore, there was infighting between the Royal Navy and Royal Air Force over the priority of their respective technologies. The Royal Navy was in the middle of NA-39, a project which would eventually yield the Blackburn Buccaneer, a low-altitude, over-water subsonic attack plane. The competitiveness between the two branches of the British Army got so tense that the Royal Navy offered to match some of the GOR 339 requirements with their NA-39 project, but only if the Royal Air Force backed down from its own project. To worsen the situation, the highly influential former First Sea Lord and Chief of the Naval Staff, Lord Mountbatten, was a strong supporter of the Buccaneer and denouncer of the TSR-2 project. The Royal Air Force had to feign disinterest in the Royal Navy's plan to avoid compromising their own. The political situation became even more complicated when a proposal was accepted and a contract granted. The Conservative Party was in power at the time. In response to the agreement, the opposition, mainly the Labour Party, used the project as an anti-expenditures rhetorical point that often dragged the ambitious aircraft development through the mud. Although several proposals were submitted, the Air Ministry mostly considered the P-17A proposal by English Electric and Short Brothers, as well as the Type 571 by the Vickers-Armstrongs merger. The Vickers-Armstrong submission was considered more substantial and more impressive due to its detailed inclusion of avionics, support facilities, and decisive logistics considering the aircraft's design, though. Yet the P-17A seemed promising, albeit less so. In accordance with the political goal of consolidating aircraft companies, the contract would be granted to Vickers-Armstrongs, with English Electric as a subcontractor. The project was announced to the public under the name of Tactical Strike and Reconnaissance Mach 2, abbreviated as TSR-2. Works were authorized by Operational Requirements 343 on January 1, 1959. This new document established two new expectations for the aircraft. It should reach Mach 2 at altitude, and should be able to fly as low as 200 feet or less. English Electric suggested a delta wing design, which was preferable, while Vickers-Armstrongs offered a better fuselage design. The plan turned into a coordinated Frankenstein-like project, being the front half built by Vickers-Armstrong and the rear built by English Electric. Under significant pressure, the companies merged, adding Bristol Aeroplane Company and Hunting Aircraft to the merger. Consequently, the 1960 contract fell to this new consortium, the British Aircraft Corporation. The plane was designed to use two Bristol Siddeley Olympus reheated turbojets. The drawn plans projected a sustained speed of Mach 2.05 at between 37,000 feet and 51,000 feet. The aircraft had some intensely sophisticated cutting-edge avionics, which contributed to its high cost. Some of its features, such as the forward-looking and side-looking radars for navigational fixing, would only become part of aviation several years later. The autopilot system was thought to be one of the most, if not the most advanced of its kind, enabling long-distance sorties thanks to the workload reduction for the pilot and crew. No prototypes were made for the project, however. The first development batch of 9 airframes served as a line of prototypes in everything but name. The decision to avoid work on prototypes had a negative effect over progress due to stringent production standards. 4 years after the project had begun, the first airframes, prototypes in all actuality, were ready, but featuring partial emissions and differing from the intended future production model. At the beginning of the TSR-2 project development, the British had sought for the plane to carry their existing tactical nuclear bomb, Red Beard. They believed the aircraft would carry out attacks on NATO targets assigned to the Royal Air Force, and wanted to be prepared regardless of weather, distance, or daylight. It was established that Red Beard could not be carried externally while at supersonic speed, leading to Operational Requirement 1177, calling for a new tactical nuke. The requirement had to be further modified in July of 1962, when a ministerial ruling determined that all tactical nukes must have a maximum yield of 10 kilotons. The Royal Air Force wanted a small tactical nuke that could be adapted to increase the yield if the norm was ever lifted. It was then decided that the TSR-2 needed to carry 4 WE-177A bombs, 2 in the fuselage and 2 under the wings. The bomb bay had to be adapted for the smaller WE-177A now that it wouldn't carry Red Beard bombs. Testing for the expensive and innovative TSR-2 was rocky at best. In February 1964, an engine exploded during a testbed run. The experts could not figure out why. Soon after, the first airframe was disassembled at a test center. This resulted in a logistical issue that postponed testing for a 3-month period. That summer, pre-flight tests began slowly due to problems with the engines and the landing gear. Another engine blew up while tested. It was discovered that the issue was rooted in the low-pressure turbine shaft malfunctioning. However, the problem was never fully resolved, and even under such conditions, the government insisted on launching the first full test flight before the 1964 election, but the Labour Party was expected to rise to power afterward. Celebrated test pilot Roland Beaumont was called on board to conduct this flight, knowing that the engines could explode. He would later state that, quote, "The first flight was more a political gesture than a logical stage in a professionally conducted technical program." The flight took place at the Aeroplane and Armament Experimental Establishment in Wiltshire on September 27, 1964. The flight was successful, but the landing gear did not retract after takeoff. That same problem persisted until the 10th test. The 14th test saw the first supersonic flight, and the aircraft reached Mach 1. By the end of the program, 24 test flights had taken place. All of these used the rudimentary and incomplete versions of the aircraft, which several test pilots repeatedly claimed were outstanding. Still, major electronic components were missing, and the aircraft was not reaching the required goal set out by OR 343. In an attempt to save costs and continue with the project, the requirements were reduced to reach a combat radius of 650 nautical miles, a maximum speed of Mach 1.75, and a takeoff run-up of 3,000 feet instead of 1,800. The US began developing the F-111 Aardvark as a competing strategic nuclear bomber in the early 1960s. According to some British engineers, the TSR-2 could have been considered superior to the F-111 in many ways. In fact, it's been suggested that, at least on paper, the TSR-2 was years ahead of anything the US was developing. So why then did the British resolve to consider the American swing wing as an alternative to the TSR-2? When this possibility came out to public light, British Aircraft Corporation employees held a strike. In response, the recently elected Labour government denied that the American plane was under consideration. At least publicly, the decision to eventually cancel the TSR-2 was made on April 1, 1965, due to projected cost overruns. Despite the earlier denials, the Labour government decided to explore the possibility of purchasing F-111s instead. The completed parts of the TSR-2 were scrapped within 6 months following the project's cancellation. Behind the scenes, it's been rumored that the US forced the British to abandon the program. However, beyond cost, Labour politics likely played a more critical role in ending the TSR-2. Only 2 out of the 9 completed airframes survived, one at the Royal Air Force Museum in Cosford, and a nearly complete one at the Imperial War Museum in Duxford. The cancellation of the TSR-2 was one of many signs that the United Kingdom's imperial decline would affect every aspect of British governance. Defence priorities and budgets were deeply cut by the pullback of British power. Additionally, the UK could no longer foot the bill for a technologically advanced military with the global reach of its past. Despite its superior flight performance, the TSR-2, if you ignore the politics, may have simply been a victim of doing one thing too well and was too specialized for the mission profiles of the future. The TSR-2 may have been the best potential aircraft to deliver a tactical nuclear strike, but it became increasingly difficult to imagine a scenario in which Britain would pull the nuclear trigger. After canceling the TSR-2, Britain backpedaled on plans to buy the US F-111 after the price rose beyond what the TSR-2 would have cost. The UK did not require an aircraft that could fulfill the TSR-2 requirements, with the addition of more mission flexibility, until 1980, when it developed the Panavia Tornado in collaboration with Italy and Germany. It was April of 1945, and Germany was in flames. The bombing raids had decimated the cities, towns, and factories where the Wehrmacht mustered its last war assets, and the Americans had almost seized Western Germany. It was then that U.S. soldiers from General Patton's Third Army were conducting mop-up operations across the Rhine when a unit of infantrymen stumbled upon a battered airfield facility. Upon entering to secure it, the soldiers were baffled by what they saw. The place was filled with aircraft unlike anything they had ever seen, and they looked almost otherworldly. A German engineer then told them that the flying wing aircraft that lacked a tail and resembled a stingray were jet-powered prototypes. The Americans immediately knew they had to seize them and destroy any evidence before the Soviets realized Germany had developed a one-of-a-kind aircraft with top-tier technology. Only they could uncover the secrets of the unique German aircraft design, dubbed the HO-229. Following the end of World War I and the signing of the Treaty of Versailles, Germany was forbidden from having a navy, an air force, and a ground army that excelled 100,000 men. Still, the Germans found clever ways to overcome these severe limitations. Money that should have been spent on developing proper military technology went to other activities, such as glider clubs, where Germans managed to discreetly continue training pilots and producing new aircraft designs. During this time, a trio of brothers, Reimer, Walter, and Wolfram Horten, began to develop some interesting tailless glider concepts. All three were avid aviation fans, and the glider clubs provided them with the tools to grow as airmen. Despite lacking a proper education on aeronautics, the Hortons were naturals. In 1934, the Hortons developed their first sailplane, the HO-1. It was a tailless aircraft with straight wings. It was followed by the HO-2, which became the basis of several flying wing design concepts. Still, the Hortons wished to develop an authentic, powerful flying wing design. And while they did so in Germany, American Jack Northrop was doing the same across the ocean. A tailless flying wing design offered a better rate of climb, increased speeds with little to no drag, fuel efficiency, and a bigger bomb load. And as the Third Reich prepared to go to war, the Hortons' work attracted the attention of Ernst Udet, director of the German Air Ministry's technical research area. Udet gave the Hortons more funds to continue their research and develop a flying wing design. The brothers then moved to Tempelhof Airport and set out to work on the HO-3 aircraft, which featured swept-back wide wings. With every prototype produced, the Hortons came closer to achieving their desired flying wing aircraft. After the loss of Wolfram during the British retreat from Dunkirk in 1940, his brothers were overwhelmed. Still, they kept working on the project, which quickly came full circle. Following his service with the Luftwaffe during the Battle of Britain, Walter Horten fully envisioned the aircraft Germany needed to win against the British. A full-fledged tailless flying wing warplane that only lacked a solid engine to power it. It was the Horten 4. As the war continued across the western and eastern fronts, Reichsmarshal of the Luftwaffe and World War II ace pilot Hermann Göring issued the 3-1000s project. The program called for the development of an extremely fast, long-range bomber that could carry a potent payload. The project's name came from the capability of the new aircraft to achieve a speed of 1,000 kilometers per hour, an approximate range of 1,000 kilometers, and carry a bomb load of at least 1,000 kilograms. In addition, this design had to be armed with two 30mm Mark 108 cannons for a fighter configuration when pitched against enemy fighter aircraft. The program was certainly ambitious, and it would not be easy to come up with a revolutionary design that could fulfill all the requisites. Still, Göring knew that this aircraft could change the tide of the war, and the optimistic Horten brothers believed that their flying wing design concept was feasible for the 3-1000s program. Consequently, they began looking for the one engine that could power their design. While they did so, the German Air Ministry approved their HO-9 design and gave them 6 months to conduct the first flight. Göring was delighted. The HO-9 then became known as the HO-229, and each prototype would be followed by a Roman numeral and a sub-designation with the letter V. Three versions of the HO-229 would be developed, and they all shared a very similar airframe and inner layout. The overall design was based on a large area wing fuselage that integrated the cockpit, engines, and armament. The Hortons swept each half of the wing 32 degrees in a line that went from the nose to the start of each wingtip, meeting with the wing trailing and edged in a tightened curve. The HO-229 center was made of welded steel tubing, while the wings comprised wooden spars covered with carbon-covered plywood sections joined by a mixture of charcoal and sawdust. The wing had a single main spar and a secondary one that was used to attach the elevons to the trailing edge. The design could withstand loads of up to 7G. Both the upper and lower surfaces of the wing stretched smoothly from the left to the right wingtip. The design seemed to come out of a science fiction story and was sleek, innovative, and unique. When no control surfaces were used, there was no protuberance on the perfectly symmetric flying wing design. Also, the tricycle undercarriage was fully retractable and stored inwards under the wing roots. Borrowing from the Hinkel HE-177 Griffin, the HO-229's nose wheel also retracted rearwards under the cockpit. Drag was practically non-existent and only manifested when the aircraft took off from the ground. In addition, the single-seat cockpit featured an ejection seat system and had excellent upper and lower visibility, but it was restricted from the sides. The HO-229B1 took to the skies on February 28, 1944, with test pilot Hans Scheidhauer at the controls. Its minor flaws would be used to perfect the aircraft with the V2 version. During the test flights, the use of wood in the wings truly paid off. Besides being the ideal choice for a country that was struggling with its metal resources, wood proved to be more resistant than metal. According to tests carried out by the Hortons, the HO-229's wings could take a beating and still fly correctly. Be it machine gun fire or a direct hit from a 20mm projectile, the HO-229's airframe could still go on. The HO-229V1 gave way to the V2 version in December of 1944. This jet-propelled model was to be powered by a 003 jet engine manufactured by BMW, but was ultimately fitted with Juncker's 004 power plants after several delays. The Hortons then had to modify the HO-229's fuselage to adequately accommodate the power plants sent by Junkers. The V2 version weighed about 9 tons, had a length of 7.42 meters, a wingspan of 16.76 meters, and a height of 2.8 meters, making it a multi-engine bomber. Luftwaffe pilot Lieutenant Erwin Ziller took the HO-229B2 to the skies in February of 1945, but he had an accident during his 4th flight. After making 3 passes at an altitude of 2,000 meters, Ziller approached the airfield to land and lowered his landing gear at 1,500 meters. One of the UMO engines then failed and sent Ziller into a spin as he descended. The pilot attempted to gain control of the aircraft, but ultimately crashed off the airfield. He passed away 2 weeks after the incident, and the V2 prototype was completely destroyed. The Hortons were shocked once again, but Germany needed their work to stop the Allied bombing. Before the aircraft crashed, the Hortons managed to get critical information about the stealth capabilities of the HO-229. Its unique wood composition and design made it perfect for absorbing radar signals by British ground radar systems. This led the German Air Ministry to approve the production of over 40 aircraft. The HO-229 concept was then given to Gotha GFW to develop a new design, and the Horton brothers turned their attention to the America bomber. By March of 1945, the U.S. Army had launched Operation Lumberjack to cross the Rhine River and advance towards Berlin. Meanwhile, Gotha was hard at work developing the Gotha HO-229V3. The company fitted the V3 with 2 Junkers UMO 109 004C turbojet engines and developed a special high-pressure suit to protect the pilots while hitting the expected service ceiling. Gotha also envisioned 4 other variants, including a 2-seat version, a fighter bomber, and a fighter with different armament configurations, including one with 4 Mark 103 30mm cannons and a bomb load capacity of up to 900 kilograms. However, the Reich's surrender and the American occupation of Western Germany brought the program to an abrupt end, and in April of 1945, General Patton's Third Army found the V3, V4, V5, and V6 prototypes. Out of them, only the V3 was almost complete, and the Army shipped it to the United States for meticulous inspection. They then destroyed the other incomplete prototypes to prevent the Soviets from getting their hands on them. Today, the only surviving prototype of the HO-229 remains at the Smithsonian National Air and Space Museum's Paul E. Garber Restoration Facility, where it awaits restoration. The Thunder Screech was an experimental American turboprop plane, created as an experimental variant of the F-84 Thunderstreak fighter jet. Development began after the Navy issued a requirement seeking a carrier fighter that could take off without a catapult, a problem still facing jet-powered aircraft at the time. Even though the Navy would cancel its order, the U.S. Air Force would absorb the project for testing. The Air Force hoped to create a plane capable of breaking the unofficial record for the fastest propeller-driven aircraft. The Thunderscreech's turbo engine was ideally suited for a supersonic propeller. At first, they promised that the aircraft would reach over 1,000 miles per hour. However, this hope was dashed soon after aerodynamic deficiencies and engine reliability issues doomed the program. Not to mention that the propeller was so loud, it reportedly made crews on the ground physically sick. Early fighter jets had issues with increased acceleration and struggled to take off on short runways. Whenever a pilot needed to hit the gas to correct an approach or perform a go-around, it resulted in a terrible situation, similar to accelerating from 5 miles per hour in a sports car at top gear. Republic's XF-84H Thunder Screech attempted to solve these issues. In 1955, they introduced a stubby high speed on the new jet. The Thunder Screech, named after the terrible noise of the supersonic prop tips when operating, resulted in the loudest and most disruptive aircraft ever built. By June 1945, the American Navy started exploiting turboprops or prop jet concept as a new solution to issues with earlier jets. The idea was that a gas turbine engine could drive a propeller at optimum revolutions per minute during flight. The power output would, in that case, be controlled by modifying the pitch or angle of attack of the blades. The turboprop engine was considered quicker and more easily manageable than a jet engine. It also provided the additional benefit of less fuel. The Navy preferred an Allison gas turbine engine created in 1944 under the label T-38. It produced 2,250 shaft horsepower with a considerable 14,300 revolutions per minute. However, a reduction gear ratio decreased it down to only around 2,100 revolutions per minute. Nevertheless, the Navy was interested in the development of Allison's two-turbine engine, the T-40, expected to generate 7,500 shaft horsepower. They believed the T-40, added to two T-38s, would result in an unbelievable aircraft. The idea was that the T-40 engines could counteract the torque, like counter-rotating propellers, making the plane more manageable while flying at low speeds. Moreover, they believed the cruising range could be extended if one of the turbines remained idle during flight. The Navy decided to request a series of aircraft using the T-40. They ordered a twin-engine bomber for their carriers, a single-engine strike plane, a 4-engine flying boat, and 2 tail-sitting VTOL fighters. The VTOL fighters were assigned to Convair and Lockheed. Still, both proved to be unfortunate designs that never progressed past the prototype stage. The 2 carrier plane contracts were awarded to North American and Douglas Aircraft. Neither proved functional due to the engine's incredible unreliability. Due to this string of unsuccessful developments, the piston-engine Skyraiders from Douglas Aircraft served in Vietnam for around 20 years past their successor's initial construction. The Air Force, in turn, initiated a contest for Aero Products, Curtiss-Wright, and Hamilton Standard to create a high-performance propeller. Only Aero Products would design a functioning prop. A strange tri-bladed air screw with wide rectangular rip blades at 12 feet in diameter, the prop was intended for a constant rotation of 3,000 revolutions per minute. This left the outer 20 or so inches of the blades at supersonic Mach 1.18 speeds. Republic Aviation's XF-84H was superficially similar to the F-84F Thunderstreak, with most similarities coming from shared parts. Still, the air intakes were placed at the wing's source, similar to the photo reconnaissance variant of the Thunderstreak. The fuselage of the new aircraft was wider to give room for the T-40 twin-turbine engine at the back of the cockpit. Furthermore, 2 lengthy extension shafts were placed through the cockpit to drive the single prop utilizing a reduction gear. Since the propeller generated such power, it also increased turbulence. To solve the issue, the horizontal tail surfaces were lifted and placed on the top of its tail fin, saving it from the prop wash. To assist with stability, another vertical fin was placed over the cockpit. Further attempts to manage the torque included moving the port side leading edge air intake closer to the starboard intake and an optional asymmetrical wing flap. The aircraft was the first to feature a fully retractable and extendable ram air turbine, which was somewhat helpful considering that the plane would struggle with various engine issues. The finished XF-84H was notably different from the F-84, and the Air Force temporarily considered changing its designation to F-106, but ultimately gave that designation to Convair's Delta Dart. The XF-84H had several revolutionary features, including its aforementioned retractable ram air turbine and its afterburner. The aircraft went down in history as the only turboprop with afterburners, which boosted output to 7,400 horsepower, allowing it to fly at supersonic speed. Unfortunately, these attributes, coupled with the afterburner, were never tested. The program was cancelled before it ever really commenced. The XF-84H prototypes were plagued by engine, drive shaft, and gearbox issues. The worst and most cumbersome aspect of the experimental aircraft was the screeching howl generated by the supersonic propeller blades. Republic manufactured 2 prototypes at its Farmingdale, Long Island plant. They were then disassembled and shipped in different containers by rail to Edwards Air Force Base to undergo testing. The first prototype's maiden flight was July 22, 1955. While the aircraft yielded fantastic results with acceleration, several issues quickly became apparent. It turned out that the engines needed 30 minutes to warm up before taking off. Solely for this reason, the Air Force deemed it unfit for combat. But furthermore, it generated intense vibration from its 12-foot diameter propeller. 2, it suffered from mechanical failures from the prop pitch gear. These 2 prototypes completed a small number of test flights, racking up a mere 6 hours, 40 minutes of flight. Only 2 civilians ever partook in the tests. One, Lynn Hendricks, refused to fly it ever again, telling a Republic engineer, quote, "You aren't big enough and there aren't enough of you to get me in that thing again." The other test pilot, Hank Beard, conducted the rest of the 12 flights. Due to engine failures and persistent vibration problems, 10 of his 11 trips concluded with emergency landings. Beard later stated the following about his experience, quote, "It became a handful. When you got it out around 400 knots, the propeller governor would start surging, and the airplane would roll rather violently. The resulting vibrations were so bad because ostensibly the entire airframe was trying to torque around its own prop shaft, making it rotate left. In contrast, the prop turned to the right. The flight experience was so terrible that neither prototype was ever flown by an Air Force pilot, giving the aircraft a lonely record in aviation history. The biggest issue with the aircraft was the noise, which gave it the nicknames Thunder Screech and the Mighty Ear Banger. While taxiing, the XF-84H could be heard from up to 35 miles away. The outer inches of the propeller blades were traveling faster than the speed of sound, even during idle thrust. This caused a recurring sonic boom that went for hundreds of yards. More so, the shockwave from the boom was strong enough to knock down anyone near it to the ground. For example, a crew chief working on a nearby C-47 was incapacitated for 30 minutes when he was knocked over by a ground run. This, coupled with the engine's considerable noise, resulted in the aircraft's ground crews being notably nauseous and reportedly suffering from headaches. Most troubling of all, one of the Republic aviation engineers had a seizure after being hit by the shockwaves. The issues were so disruptive that it even affected operations at the control tower for Edwards Air Force Base, almost damaging sensitive components through the vibrations. As a solution, air traffic controllers had to turn off several devices and detect the plane via light signals held by personnel. As no one wanted to be an unintentional victim of the shockwaves, this direction resulted in multiple complaints. As the Air Force Flight Test Center received more and more complaints, they ordered Republic Aviation to tow the plane out to Rogers Dry Lake before test flights so it didn't disturb anyone. The wide array of issues resulted in no further testing beyond Phase 1. The Air Force canceled the program in September 1956. The Guinness Book of Records reported that the aircraft was the fastest propeller plane ever constructed. Its design had a top speed of 670 miles per hour. Its tests supposedly yielded a maximum speed of 623 miles per hour. The claim has been repeatedly disputed for its inconsistency with the data collected by the National Museum of the U.S. Air Force, which marks the top test speed at 520 miles per hour. The 1989 Rare Bear version of the Grumman F-8F Bearcat holds a more established record of 528 miles per hour. Once it became evident that the aircraft would not work, except when attempting to land on deck, they decided to back out of the project. Only 2 prototypes were ever built. Although Republic Aviation had estimated that the XF-84H would be capable of reaching a top speed of 670 miles per hour, it never achieved an in-flight speed above 450. Had it successfully performed as intended, it would have become the fastest propeller airplane ever. Instead, the Russian Tupolev Tu-95 holds that record for its capability to cruise at 545 miles per hour, with a top speed of 575 miles per hour, due to its 4 14,800 horsepower turbo propellers. One of the 2 prototypes went on to serve as a gate guard at the airport in Bakersfield, California, until it was sent to the National Museum of the U.S. Air Force in 1992. It remains there to this day. The McDonnell Douglas F-15 Eagle is one of America's most prominent air superiority fighters, credited with over 100 air victories without suffering a single loss to this day. First flown in 1972, it is still currently in service with the United States, Israel, Japan, and Saudi Arabia. Even before the first batch of F-15s rolled off the assembly line, the U.S. Air Force and NASA began experimenting with the fighter. In 1984, an F-15 was highly modified with short takeoff and landing capabilities, reducing the aircraft's required runway landing length by an impressive 80%. Years later, specialized canards developed by NASA drastically improved the aircraft's stability at supersonic speeds and even implemented artificial intelligence for emergency protocols. The result was the most modified F-15 ever built, with state-of-the-art components and systems that made it a more effective air superiority fighter that even helped test and discover new technology. It would also go down in history as the Frankenstein aircraft. The F-15 Eagle twin-engine, all-weather tactical fighter aircraft was initially developed to replace another fighter produced by McDonnell Douglas, the F-4 Phantom II, used extensively during America's involvement in the Vietnam War. When the conflict ended, the Navy wanted a new aircraft capable of outclassing the recently introduced Soviet MiG-25. This led to the TFX or FX program, which aimed to develop a powerful air superiority fighter. The Air Force then awarded several contracts, eventually declaring McDonnell Douglas the winner. After numerous redesigns, the F-15 was formally introduced into service in 1976 and would span several variants as the years went by. The basic variant had an all-metal fuselage, a large cantilever, and a shoulder-mounted wing with a crop delta shape and a 45-degree leading-edge sweep-back angle. Mounted in the forward fuselage, its cockpit featured a large canopy with a one-piece windscreen that provided excellent visibility for the pilot. 2 Pratt & Whitney F-100 turbofan engines with afterburners supplied over 23,700 pounds of force, allowing the F-15 to achieve a maximum speed of 1,650 miles per hour at high altitudes and 921 miles per hour at sea level. Moreover, it had a capacity for over 13,450 pounds of internal fuel, with an estimated combat range of 1,220 miles. The Eagle has a total length of 63 feet, a wingspan of 42 feet, a height of 18 feet, and a maximum takeoff weight of 68,000 pounds. It can also be fitted with numerous weapon configurations, including one 20mm M61 Vulcan cannon and 9 hardpoints for Sparrow, Sidewinder, AMRAAM, and other missiles. Before its introduction, Douglas and several other agencies began working on innovative variants of the F-15, given its wide array of configurations. In 1975, NASA's Langley Research Center began studying two-dimensional thrust vectoring nozzles. 2 years later, Langley started researching 2D nozzles, thrust vectoring, and thrust reversing on an F-15. By 1984, the Flight Dynamics Laboratory of the Air Force Aeronautical Systems Division had awarded McDonnell Douglas another contract to develop an F-15 prototype that could take off and land on short or severely damaged runways. The objective behind the prototype followed a simple scenario. If the USSR ever attacked the US or NATO, airstrips would be the first targets. As such, the Air Force had to be ready for combat before the Soviets bombarded its airfields. This led to the F-15 STOL MTD platform, or Short Takeoff and Landing Maneuver Technology Demonstrator Aircraft. According to aviation expert Alex Hollings, the ideas behind F-15s taking off from damaged runways were bolstered by thrust vector controls that allowed the pilot to aim the outflow of thrust from the aircraft's engines. The F-15 STOL MTD used a two-directional thrust vector control that allowed the pilot to orient the outflow of thrust up to 20 degrees up or down. Hollings added, quote, "That vector control of the engine outflow was further supported by the addition of canards in 1988, just in front of the F-15's traditional wings. The canards were modified horizontal tail surfaces stolen from the FA-18 Hornet. With such enhancements, the F-15 prototype managed to take off at speeds as low as 42 miles per hour, reducing the runway length by over 25%. Moreover, the engineers leveraged thrust from the F-15's engines, canards, and thrust vector control to reduce the landing runway length by almost 80%. Compared with a standard F-15, which required over 7,500 feet of clear runway to land properly, the modified prototype only needed 1,650 feet. In 1993, the United States Air Force handed the keys to its highly modified dogfighter to NASA. The aircraft was chosen as the central element of the service's Advanced Controls Technology for Integrated Vehicles, or ACTIV program. The test program was carried out at the Dryden Flight Research Center, and its main goal was to develop and demonstrate advanced engine and aircraft flight control technologies that would significantly enhance the aircraft's engines and operational capabilities via flight and ground tests. The information learned from the study would then be used for the next generation of high-performance fighters. However, the aircraft needed to undergo yet another series of modifications for this objective. While NASA opted to retain the unusual wing layout of their new F-15, the engineers installed special Pratt & Whitney pitch-yaw balance beam nozzles, complete with a new set of engines, the F-100 PW229. Unlike the previous thrust vector control systems used under the Air Force's STOL MTD program, these movable nozzles offered an entire 360-degree arc through which they could redirect outflow. Additionally, the aircraft was equipped with a flight test nose boom, configured with angle of attack, and two canards in the upper inlet area forward of the wing. Combined, all of these systems turned the aircraft into the best F-15 in the world. According to official NASA documents, the active aircraft's flying qualities significantly outshined other production F-15 aircraft. The tests began in 1995 and were mainly flown by test pilots Larry Walker and Roger Smith. During the process, NASA officials estimated that stability at supersonic speeds was improved by a factor of over 100% due to the addition of the new front canard. All nozzle test points were accomplished successfully and safely, without any significant problems or unanticipated hazards, while the pitch-yaw balance beam nozzles proved to be a successful design that provided modern fighter aircraft with efficient thrust vectoring capability. These movable features also reduced drag and increased fuel economy or range compared with conventional aerodynamic controls. The F-15 active program tested other flight systems that were later used in the F-15E Strike Eagle, a highly used variant intended for air-to-ground engagements. NASA eventually modified the cockpit of the testbed F-15 to match that of the F-15E. And while the active program ended in 1999, the F-15 still had a few years left with NASA. In late 1999, Dryden Flight Research Center initiated another program to investigate possible applications of artificial intelligence, or AI, to reduce a pilot's workload after a flight control failure. The program was defined by NASA as the Intelligent Flight Control System, or IFCS. The aim was to prove that AI and state-of-the-art control algorithms could result in effective self-healing control software. NASA's purpose was to help a pilot control his aircraft under dangerous conditions such as mechanical and electrical failures, mid-air collisions, battle damage, or even unexpected bird strikes. In other words, the IFCS program was designed to adapt to damage, stabilize the wrecked aircraft, and restore its handling qualities with the help of adaptive AI technology. The ambitious program ran until 2008 and involved the Georgia Institute of Technology, NASA Ames Research Center, the Institute for Scientific Research, and Boeing Phantom Works. Meanwhile, the highly modified F-15 Active was chosen for the new self-healing flight control system technology. According to writer Rodney Rodriguez, quote, "The dual AI of the IFCS was composed of a pre-trained static neural network, which provided the basic aircraft aerodynamic derivatives for each flight condition, and a dynamic cell structure neural network, which was meant to be trained online by a parameter identification algorithm, which provided observations of the actual expected aerodynamic derivatives of the aircraft." The system was tested successfully and gave NASA valuable information about advanced adaptive flight control systems. Some of these ideas were eventually incorporated into modern fifth-generation fighter aircraft, like the Lockheed Martin F-35 Lightning II. The F-15 model that served in the short takeoff and landing, active, and intelligent flight control system programs was used as a testing platform for a total of 2 decades. Throughout all of its iterations, the F-15's front canards and thrust vectoring power, along with its classic red, white, and blue paint job, remained unchanged. The objective behind all the testing was never to be added to the F-15 Eagle, but rather to test certain capabilities that the United States Air Force and NASA could develop for further generations of fighters. In doing so, both services proved that the F-15 was, and still is, one of the most iconic and adaptable aircraft in United States history. Moreover, despite never firing a shot in anger, the McDonnell Douglas F-15 STOL MTD remains one of the most significant Eagles. After years of testing and modifications, the F-15 STOL MTD active aircraft was retired in January of 2009. At the time, that particular aircraft was the oldest F-15 still flying. While the most well-known Cold War-era military jet aircraft came from Britain, the United States, and the Soviet Union, Sweden quietly developed what would become the most advanced fighter jet in Europe at the time. The Saab 37 Viggen was a mighty machine with a name that alluded to millennia-old Norse mythology, and it was easily recognizable as it was the first canard design aircraft produced in quantity. The historic aircraft could fly steadily at speeds above Mach 2 at high altitudes and operate from short runways, ready to serve their home country at a moment's notice. And despite Sweden maintaining a strict policy of neutrality at the height of the Cold War, its pilots were willing to risk their lives to do the right thing if a nuclear conflict with Russia were to explode, with their Viggens more than ready for battle. In the early 1950s, Saab Aerospace Company developed the Draken, an aerodynamically advanced fighter that made its maiden flight in 1955. After this achievement, the Swedish Air Force immediately began setting the requirements for its next generation of combat aircraft. Expected to fly no earlier than the mid-1960s, the new aircraft was planned to be adaptable for all tactical mission roles, with an integrated weapons system that would operate in conjunction with Sweden's national electronic air defense system, Strill 60. One radical requirement for the proposed aircraft was its ability to operate from short runways only 1,640 feet long as part of the Baz 60 airbase system. Introduced in the late 1950s and developed by the Swedish Air Force during the Cold War, Baz 60 revolved around the forced dispersal of many aircraft across several World War II airbases, including road runways acting as backups. Other requirements included having high maneuverability and low turbulence sensitivity at subsonic, low-level flight, Mach 2 performance at high altitude, and the ability to be easily repaired and serviced, even for personnel without much training. Enabling so many operations imposed plenty of critical demands on the design. As such, over 100 different concepts were examined in previous studies, to develop the best possible aircraft with single and twin-engine configurations, traditional and double delta wings, and canard installment. In 1960, the United States National Security Council, led by President Dwight D. Eisenhower, presented Sweden with an irresistible proposition: the 37NX Military Technology Agreement, in which American officials promised military help in the event of a Soviet attack. As part of the agreement, Swedish engineers were allowed access to America's latest aeronautical technology, and the interactions made it more possible for Saab to design a faster and cheaper aircraft. Then, in December of 1961, the Swedish government approved the development of Aircraft System 37. Built at the height of the Cold War, when a potential Russian attack was a genuine concern, this was by far the largest industrial development task ever attempted in Sweden. By 1962, most of the project's elements were either finished or close to being fully developed, including the power plant, ejector seat, arms, reconnaissance systems, training equipment, and the fighter itself. A development contract was subsequently signed in the fall. The daunting venture accounted for 10% of all Swedish research and development funding throughout the decade. The Saab 37 Viggen was a single-engine, short-medium-range combat aircraft with a highly advanced aerodynamic configuration for its time, a radical design featuring an aft-mounted double delta wing. In addition, the aircraft had small, high-set delta-shaped canard foreplanes, and the Saab model became the first mass-produced aircraft to ever feature them. The name Viggen had two distinct meanings. The first referred to Axvik, which is historically translated to thunderstones. In Norse mythology, an Axvik is what the Viking Age inhabitants of Scandinavia called the prehistoric stone axes. Sent by the god Thor in lightning strikes, these axes were believed to have magical properties, like lightning protection. The second interpretation came from vik, the Swedish word for tufted duck, in reference to its canard configuration, canard being the French word for duck. While Saab originally planned to power the Viggen with a single Rolls-Royce Medway engine, the aerospace company chose to license the Pratt & Whitney JT8D engine when its development was cancelled, and created a modified version of it, the Volvo RM8. To keep the landing distance short, the Saab 37's airframe included a thrust reverse to help slow the aircraft down. A one-of-a-kind creation in single-engined aircraft, the thrust reverse could be used to taxi backward, similar to a car. While backing up, however, the pilot needed to be careful not to use the wheel brake toe pedals, as the aircraft could easily tip over. Since the early design period, Saab engineers decided that the Viggen should replace the workload and performance of a second crew member with a digital central computer and a heads-up display. The computer, called Central Calculator 37, was the world's first airborne machine to use integrated circuits, supporting the pilot by performing functions such as navigation, flight control, and weapon aiming calculations. As originally planned, the first Saab 37 flew in 1967, with the company's chief test pilot Erik Dahlström at the controls. Dahlström described the new jet as easy to control. The Swedish government initially planned for 800 Viggens to replace all their other combat aircraft in service. However, a mix of inflation and several eventualities reduced the total to 329. The first Saab 37 Viggen was delivered to the Swedish Air Force in July of 1971. At the time of its introduction, the Viggen was the most advanced fighter jet in Europe. Conversation training for the new Viggen pilots included a minimum of 450 flight hours, including other models, the Viggen, and several simulators that were seen as a decisive factor in the ease of conversion to the type. By 1974, Sweden's newest fighters' safety and reliability levels were above expectations. And while the Saab 37 wouldn't see combat service, it would prove to be a safe, reliable, and easy-to-maintain aircraft. The finished product was an outstanding performer, capable of hitting 1,386 miles per hour, climbing at 40,000 feet per minute, and reaching a total service ceiling of 59,000 feet. For armament, the jet carried one 30mm Oerlikon KCA cannon with 125 rounds, and had 3 hardpoints under each wing, plus 3 under the fuselage. One of its only significant issues happened during low-level flight, in which birds constantly threatened the system. To counter this, the Swedish Air Force paid closer attention to their migratory patterns. By then, The Swedish Air Force had 2 operation squadrons working with the Viggen, with a third ready for training. In addition, there were multiple versions of the type. The 2 primary ones were the AJ-37 ground attack version, which could carry up to 15,500 pounds of weapons load on 9 hardpoints, and the late JA-37 all-weather interceptor version. Other variants served as strike fighters, aerial reconnaissance or maritime patrol aircraft, and a 2-seat trainer. In the height of the Cold War, when East-West tensions were at their highest point, Viggen pilots flew approximately 500 live quick reaction alert or QRA missions per year to intercept any unidentified aircraft approaching Swedish airspace. These targets came from both Warsaw and NATO nations flying close to Swedish airspace over the Baltic Sea and near the Gulf of Bothnia. Still, the most challenging QRA targets were the United States Air Force's Lockheed SR-71 Blackbirds, with a reputation of being uncatchable and able to outrun missiles. The SR-71's impressive performance capabilities provided a unique opportunity for Viggen pilots to evaluate and experiment with several intercept solutions against high-speed, high-altitude threats. By the mid-1980s, the Swedish pilots managed to achieve radar lock-on with radar on the SR-71 numerous times by using the predictable patterns of the Blackbird's routine flights over the Baltic Sea. Soon after, in June of 1987, a Blackbird, flown by Lieutenant Colonels Dwayne Knoll and Tom Veltri, experienced a sudden engine failure during one such mission. While flying over the neutral waters of the Baltic Sea near Soviet territory, one of the jet's powerful Pratt & Whitney J58-1 afterburning turbofan engines lost power. The crew had no choice but to descend to 25,000 feet over Swedish airspace, and the men were left in a vulnerable position. Suddenly, the Blackbird was intercepted by 2 pairs of Swedish Saab 37 Viggen fighter jets, which protected the spy plane and ensured that no enemy fighter would try to harass it. The 4 Swedish pilots proved to be guardian angels for the crew of the SR-71. At the time, the Soviet Air Force had a squadron of MiG-25 PD Foxbat high-speed interceptors based in East Germany, which were regularly sent to try and intercept the Baltic Express to no avail. Still, no details of the 1987 encounter between the SR-71 and the Saab 37 Viggens were published until 3 decades later. In the 1990s, several major avionics upgrades were made to the aircraft, now designated as the JA-37D variant, including a more updated computer. By then, however, it was slowly being replaced by the newer Saab JAS-39 Gripen, with the last active model of the Saab 37 Viggen retired in November of 2005. Still, a few models were used for electronic warfare training against the Gripen, and their last official flights happened in 2007. 10 years later, in a ceremony in Stockholm on November 28, 2017, United States Air Force officials presented all Swedish pilots with air medals for their brave actions during the Cold War. The Northrop Grumman X-47B was a successful step in the U.S. Navy's quest to build the first carrier-capable unmanned aerial vehicle. After the promising Pegasus project of the early 2000s, the service teamed up with its industry partners and developed a truly outstanding piece of engineering, a strike fighter-sized drone. Throughout the 2010s, the X-47 underwent several modifications and a subsequent series of special tests that not only proved the concept was feasible, but demonstrated the machine's reliability. The expectations were sky high, and it was now time to prove if such advanced technology could be readily exploited, or if the mighty UAV was too progressive for its time. Until the 2000s, the U.S. Navy was not fully committed to developing a practical unmanned combat air vehicle, let alone one that was carrier-based. But then, the Sea Service partnered with the Air Force, Boeing, and Northrop Grumman in a concept exploration program led by DARPA to come up with a single solution for both services. The specifications called for an aircraft capable of deck launch and recovery, integration with command and control systems, and viable operation amidst a carrier's electromagnetic interface. Needless to say, the airframe had to withstand the corrosive effects of salt water. The Navy's interests included deploying the UCAV for reconnaissance missions as a means to penetrate into protected enemy airspace and identify targets for upcoming raids. Hence, in early 2001, the service awarded a contract to Northrop Grumman to develop an unmanned combat air system demonstrator that would be known as the X-47 Pegasus. The resulting demonstrator turned out to be a simple black arrowhead without a vertical tailplane. It had a leading-edge sweep of 55 degrees and a trailing edge of 35 degrees, and 6 control surfaces with 2 elevons and small flap structures. Plus, it was powered by a single Pratt & Whitney Canada JT-15D5C small high-bypass turbofan engine. While the flight test program did not involve weapons delivery, the aircraft was equipped with 2 weapons bays able to carry a 500-pound dummy bomb to simulate operational loads. Besides, the Pegasus would evaluate technologies for carrier deck landings. Nevertheless, the joint endeavor was terminated in 2006, and each service proceeded with its own projects. Consequently, the Navy selected Northrop Grumman's proposal for further development. Following the proof-of-concept demonstration, a full-size technology demonstrating UCAV was born. It had the exact same size and weight as the projected operational aircraft to carry out more realistic tests, and the X-47B would also have a complete weapons bay to carry existing missiles. The Sea Service went through with the undertaking as part of the X-47 initiative, which took almost an entire decade. In late 2008, the Air Vehicle 1 prototype was completed and rolled out in Palmdale, California. But further work was needed due to its software's complexity. A year later, the aircraft underwent active towed taxiing tests, but didn't actually try taxiing under its own power until early in 2010. Formal flights started later than initially planned, with the first flight taking place in early 2011 at Edwards Air Force Base. However, the first flight performed in cruise configuration, with its landing gear retracted, wouldn't happen until the fall. Meanwhile, AV-2, the second demonstrator, first flew towards the end of that same year. Although the 2 demonstrators were initially planned to go through a 3-year test program, their performance was so consistent that preliminary tests ended after barely 16 flights. Soon after, the Navy continued with sea trials, namely carrier launches and recoveries, and also autonomous in-flight refueling. The models were eventually refitted with aerial refueling equipment and software for the next stages. Notably, they were never armed. Then, as the test crew continued refining the remote control techniques required for proper routine functions, akin to a piloted aircraft, the engineers' most significant challenge became overcoming the maritime environment's corrosive effects on the vehicle's exposed surfaces. In early 2012, the company tested a wearable remote control system that allowed ground crews to manually steer the drone along the deck. Then, halfway through the year, the model began high-intensity electromagnetic interference testing. Aircraft carriers represent perhaps the most complex electromagnetic spaces on any surface ship whenever their multiple radars and systems are switched on. The X-47B initialed its carrier-based evaluation aboard USS Harry S. Truman in November, and in less than a month, the prototype successfully completed the first at-sea test phase. Fortunately, the aircraft proved to be compatible with the carrier's flight deck, hangar bays, and communications systems. By the summer of 2013, the X-47B performed an arrested landing on a simulated carrier deck at Patuxent River, Maryland, and a few days later, it launched from USS George H.W. Bush, marking a milestone in drone development, as it was the first time a UAV was catapulted off an aircraft carrier. After launching, the UAV was transferred over to a second pilot, who flew it successfully from the Chesapeake Bay to Naval Air Station Patuxent River. Later, it also proved capable of achieving touch-and-go landings and takeoff from the deck while underway. The X-47B also accomplished the first arrested landing of a UAV on a carrier at sea, further propelling the program forward in its mission to create the first carrier-operational drone. However, the model had a technical issue during the third try and was diverted to the Wallops Flight Facility in Virginia. As one of its 3 navigational subsystems failed, the remaining 2 identified the problem and alerted the operator, who followed the protocols to abort the landing attempt. The mishap ended up proving the drone's reliability and autonomy. Like many other popular drones across the globe, the device's design featured a defined triangular shape. Moreover, the aircraft was a true flying wing, given that it didn't appear to have any obvious vertical surfaces, similar to the Northrop Grumman B-2 Spirit stealth bomber. As for its power plant, a single Pratt & Whitney F100 220U turbofan engine was buried within the fuselage, and it aspirated through a shallow duct along the forward spine, while the exhaust went through a specially designed port at the rear. Evidently, the lack of a pilot housed in a typical canopy left room for significant internal volume, which could be taken advantage of when carrying specialized mission equipment, armament, and fuel stores, or additional avionics and subsystems. Production units would be fielded with 2 internal weapons bays, just like the Lockheed F-22 and F-35 fighters, and its capacity amounted to 4,500 pounds of ordnance, with guided munitions being its most likely load. Furthermore, its carrier-based capabilities demanded key qualities integrated into its design, namely the folding of its wings for easy storage, a reinforced undercarriage with an arrestor hook, and corrosion resistance to counter the effects of its hostile environment. The X-47B's undercarriage was retractable and consisted of 2 single-wheeled main legs and a twin-wheeled nose leg. The drone's flight system is autonomous, and its navigation is handled by a hybrid vision-based global positioning system. Meanwhile, its flight path is pre-programmed, while it operates under the supervision of a mission operator. The device has a 62-foot wingspan, or less than half when contracted, a length of 38 feet, and a height of 10.4 feet, and it can reach a cruising speed of 685 miles per hour, or a high subsonic speed of approximately Mach 0.45. Plus its operational range exceeds 2,100 nautical miles. Likewise, the X-47B managed to reach a ceiling of roughly 40,000 feet. The drone was also fitted with electro-optics, infrared, synthetic aperture radar, inverse SAR, ground moving target indicator, electronic support measures, and maritime moving target indicator sensors, while its airframe and internal systems eventually incorporated stealth characteristics or low observable relevant requirements. The UCASD program demonstrated the feasibility of operating drones on an aircraft carrier at the cost of $813 million. By the spring of 2015, the fighter-sized drone successfully completed the first-ever autonomous aerial refueling demonstration, and shortly after, the primary test program was finished. Still, roughly a year later, the Navy decided to convert the previously surveillance and strike-capable aircraft into a reconnaissance aerial refueling UAV with limited strike capability. The subsequent unmanned carrier-launched airborne surveillance and strike project was cut off in favor of the MQ-25 Stingray carrier-based aerial refueling system, or CBARS. For all its success, the X-47B eventually raised concerns about its costs and proved insufficiently stealthy for the project's needs. There was an initiative to convert the demonstrators into museum exhibits, but the prototypes remained in active flying condition instead, allowing for subsequent evaluations and variants. In late 2017, the X-47B proved useful as a testbed for the MQ-25 proposal, but Northrop Grumman soon retired from the competition. Both UAVs remain stored in a hangar and are only used for upkeep static engine runs out of the public view. Still, the technology and expertise gained from the remarkably successful venture earned much recognition and awards, like the 57th Annual Laureate Award for Extraordinary Achievements in Aeronautics and Propulsion, hosted by Aviation Week, and the 2013 Collier Trophy for Excellence in Aeronautic Technology by the National Aeronautic Association. Furthermore, the X-47B's legacy was passed down to the X-47C, which may restore its predecessor's honor, should it meet the stealth requirements the Navy expects from it.